You know, every once in a while, a paper comes along that feels like it's pulled straight from science fiction. Well, back in 2017, a couple of researchers from Google Brain published exactly that. They ask a really fundamental question. What if an AI could actually learn how to design other AIs? This work, Neural Architecture Search with Reinforcement Learning, was so much more than just another paper. It was a real turning point. It was the moment AI started to automate one of its toughest, most creative jobs, designing itself.
Okay, so here's how we're going to break this all down. First, we'll look at the big problem that got this whole thing started. Then we'll dive into the absolutely brilliant idea they came up with, an AI to design AI. We'll see how it actually learns, check out the results where it went head-to-head with human experts, and finally, talk about the massive legacy this paper left behind and what it means for the future.
So, to really get why this paper was such a big deal, we got to rewind the clock to the mid-2010s. Deep learning was just exploding, right? But all that progress was basically riding on the shoulders of a small, elite group of human experts who were painstakingly designing these neural network architectures by hand. And that, right there, was the bottleneck.
And hey, don't just take my word for it. The authors said it themselves. Designing these systems wasn't really a science. It was more like an art. It was all about intuition, endless trial and error, and years of really specialized experience. The field desperately needed a way to grow beyond the limits of just a few brilliant minds.
You know, this pressure cooker had been building for years. The whole focus of AI research had done a complete 180. Back in the 2000s, people were handcrafting features for images, things like SIFT and HOG. But then, AlexNet changed the game in 2012. The paradigm completely flipped. Suddenly, the architecture itself was the thing that learned the features. This launched a golden age of incredible handcrafted networks, but man, the pressure to invent the next big thing was just immense. So Zofin Lei came along with this totally radical idea. What if we could just automate the architect? What if we could build a system that learns how to design amazing neural networks all on its own, from scratch? And that was the core concept behind Neural Architecture Search.
This question right here, this is the heart and soul of the paper. It's this incredible leaps towards something called meta-learning, or basically learning to learn. Instead of just training a network to, say, classify cats and dogs, they were training a network to generate the blueprints for other networks. It's just a wild leap in how you think about the problem.
Their system has two main parts, and the best way to think about it is like a master architect and an apprentice builder. The controller is a recurrent neural network. That's our master architect. Its whole job is to propose blueprints for new networks. Then you have the apprentice, the child network. It takes that blueprint, gets built, and then gets trained and tested on a real task.
So what does one of these blueprints actually look like? Well, the controller RNN literally generates a sequence of instructions, basically a long string of choices. It decides things like, okay, the filter height should be 5, the width should be 5, let's use 48 filters and a stride of 1. It does this for every single layer, literally writing out the entire recipe for a brand new AI.
Okay, but just spitting out random recipes isn't enough. How does the master architect actually get any good at its job? It can't just guess forever. And that's where the reinforcement learning part of the paper's title comes into play. The whole system is built on a really powerful feedback loop that lets the architect learn from experience. At the very beginning, the controller is, well, pretty clueless. It's just throwing spaghetti at the wall. Its designs are random, and frankly, most of them are terrible. But after thousands and thousands of tries, it starts to get a feel for it. It develops an intuition, learning which patterns and combinations are likely to lead to a high-performing network.
So how does it learn what's good? The feedback it gets is actually super simple. It's just the accuracy of the child network it designed. Once an apprentice network is built and trained, they test it and measure its performance. That accuracy score becomes the reward. The higher the accuracy, the bigger the reward for the controller. Simple as that.
The whole learning process uses an algorithm called reinforce. So step 1, the controller suggests a design. Step 2, the child network gets built and tested. Then its final accuracy is used as a reward to update the controller. This just gently nudges the controller to be a little more likely to suggest good designs like that in the future. Now here's the kicker. They repeated this loop more than 12,800 times.
And a search that massive? Well, that's computationally insane. You're not doing this on your gaming PC. To even make this possible, they ran the whole experiment on a massive scale, training 800 child networks at the same time on 800 different GPUs. This was a true brute force approach, the kind of thing only a handful of places on Earth could even dream of attempting back then.
So, after all that theory, after all that mind-boggling computation, did the thing actually work? Well, this is where we get to the results. And honestly, this is where the paper just becomes legendary. Because the AI architect wasn't just a cool idea. It delivered state-of-the-art results. Let's look at this CFAR-10 image classification task, a classic benchmark. The best human-designed model at the time was something called DenseNet, and it had a test error of 3.74%. The network discovered by Neural Architecture Search, or NAS, came in with an error rate of 3.65%. It had set a new state-of-the-art. The AI had officially beaten the best human architects at their own game.
And get this, it wasn't just a tiny bit more accurate. The AI design model was also 1.05 times faster than the human design one it just beat. So it was not only better, it was also more efficient.
But to really prove this wasn't just some fluke for image tasks, they pointed their system at a totally different problem: language modeling. Their goal was to design a new recurrent cell, which is the basic building block for networks that handle language. And what happened? The same thing. It blew past the human-designed state-of-the-art. And this result is just beautiful because it shows how powerful the method is. It got a 3.6-point improvement in something called perplexity. For language, just think of it as a prediction score, where lower is better. Now, a drop of 3.6 might not sound like much, but on a really tough benchmark like this, that is a massive, massive leap forward. It proved the AI architect was a generalist. It could cook up novel solutions for completely different kinds of problems.
The shockwaves from this paper went way beyond just topping a few leaderboards. Its publication wasn't just another update for the field. It was an origin story. It literally gave birth to an entire new subfield of machine learning research.
I mean, the legacy is just immense. First off, it created the whole field we now call neural architecture search, automating a huge bottleneck in how we develop AI. It also kicked off a giant wave of new research, with everyone trying to figure out how to do NAS faster and cheaper. And the work was so practical that the new recurrent cell it discovered, the NAS cell, was added directly into TensorFlow for anyone to use. This all leads us to our final section, the future. Because this paper didn't just solve a problem, it opened a door to a much bigger, much wilder idea. If an AI can learn to design an architecture, what else could it learn to design? And this is the really mind-bending question the paper leaves us with. We've just seen an AI play the role of an architect. But could a future version play the role of a scientist? Could it design not just the network, but the learning algorithm itself? Maybe a better version of gradient descent? Could it go even further and discover some fundamental new principle of learning that we humans have completely missed? That is the grand challenge that Neural Architecture Search set into motion.
This is for entertainment purposes only.